So let's see. Good morning. How are you? So do you have any questions or comments before we begin? Okay, I can remind you that the first homework is due in 2 days on Wednesday, and the next one is due after that on Friday. The first homework is very short, but the next one is 7 questions. Let's see. Anything? All right, so were you able to see the video that I posted on Friday? Very good. So that's the first type of equations that we study in this course, separable equations. And as I said during the introduction, by some coincidence, around half of the equations that you may encounter in practice are separable somehow. So this is just a coincidence perhaps, but it's a good one because we know how to solve separable equations. So here are some more examples from the previous course. All right. I just want to make sure by giving more examples that you have seen enough examples to know how to solve these equations. So, all right, so here is a pretty straightforward example. Y prime is equal to y plus 1 quantity squared. So this is a separable equation, but can you please tell me what the order of the equation, whether it's linear or not, and whether it's autonomous or not?
The order is first order.
Yeah, it is first order. Very good.
Is it linear?
No, it's not linear. Can you tell me why it's not linear?
Because y is equal
No, that's an answer to the third question. Yeah, it is autonomous. Yeah.
oh, is it because it's not like equal to 0?
No, it's nonlinear because of the square, because it's y plus 1 squared. So y plus 1 squared is a quadratic function. It's definitely nonlinear. Yeah, you're multiplying y and y. All right, so now let's solve this equation. We see that it is separable because it fits the definition of a separable equation. I mean, it's written as a separable equation. So an equation is separable when it is, or when it can be written in the form y prime is equal to some function of x times some function of y. Here, the function of x is missing, but we can say that it's 1. So we can say that this is 1 times y plus 1 squared. So 1 is a function of x, and y plus 1 squared is a function of y. So this is a separable equation, and then standard way to solve it is that we divide by the function of y. So we have y prime over y plus 1 squared is equal to 1. So all the terms involving y are on the left-hand side, and all the terms involving x are on the right-hand side. So now we integrate both sides as functions of x. And so we have integral of y prime over y plus 1 squared dx is equal to integral of y on dx. Integral of 1 is just x plus a constant. And On the left-hand side, we make a substitution. So under the integral, we replace the variable x by the variable y. And then dy is equal to y prime dx. So this is by the substitution rule. Yeah, we have to consider, that's right. We have to consider a case when y is equal to -1. Right. So you're right. The only way we can do this division is when y is not equal to -1, because otherwise we would be dividing by 0. So we have to consider that case separately. Yeah, that's right. But yeah, so I'm going to say that on the next page. So now the integral of dy over y plus 1 squared. So we made the change of variable. Y prime dx is dy. So the integral of dy over y plus 1 squared is -1 over y plus 1. So right. So on both sides we can get some constant, because the antiderivative is only unique up to a constant. So here I wrote the constants on both sides. -1 over y plus 1 plus a constant is equal to x plus another constant. And then the two constants may or may not be the same. So let's consider the difference of the two constants. So I subtract the constant on the left-hand side from the one on the right-hand side. So we're left with just one constant, the difference of those two constants. So -1 over y plus 1 is equal to x plus c3. Okay. And now let's solve for y, because we want to find y. So y plus 1 is equal to -1 over x plus c3. So I guess I cross multiplied or whatever, and we got y plus 1 is -1 over x plus c3. So y is -1 over x plus c3 minus 1. Okay, so and now, as you well pointed out, there is one more solution that we missed by applying this process. Namely, in order to divide by y plus 1 squared, we need y plus 1 squared, or y plus 1 to be non-zero. So when we did that, we missed the solution y is equal to -1. So y is equal to -1 actually is also a solution, which we need to check. Why is it a solution? Because so the constant function y is equal to -1. When we plug it into the equation, the derivative of a constant is 0. So if the solution is the constant function -1, his derivative is 0. And then on the right-hand side, -1 plus 1 quantity squared is also 0. So this actually is a solution, which we need to check. So in general, the solution is either -1 over x plus a constant -1, or the constant function -1. So this is how we solve this equation by the separation of variables. Any questions about this example? So this is the general solution of the equation. All the solutions of this equation are either of the form -1 over x plus a constant -1, or the constant function -1.
Where does that constant solution
This one, y of x is equal to -1. So that's exactly what you pointed out a couple of minutes ago.
I know, but like, how do you work that out? Just to say that, like, oh, there's a x squared sine x.
So So the way that you see it is that either y is not equal to -1, in which case you can divide by y plus 1 squared and you get this part of the solution, or y is equal to -1, and then you have to check that the constant function -1 is a solution. And because of the uniqueness of solutions to this equation, once we have checked that the constant function -1 is a solution, so this tells us that there are no solutions which are -1 half of the time and given by another expression the rest of the time. So once we check that the constant function -1 is a solution, this means that this is the only solution that corresponds to the initial value -1. Otherwise, the solution would have been non-unique. So, I mean, can the solution be, let's say, -1 on some interval and x on some other interval? No, because the solution is unique, as we'll see by the existence at uniqueness theorem, maybe 2 or 3 weeks. And then once we establish that -1 is a solution, this means that -1 is the only solution, corresponding to the initial value -1. So now let's find the particular solution that corresponds to various initial values. So this is an example of an initial value problem. Y prime is y plus 1 squared with the initial condition y of 0 is equal to 1. So if the initial condition is y of 0 is equal to 1, this means we are not dealing with the second solution here, which is y of x is equal to -1. Because if the solution is constantly -1, this means it's never equal to 1. Because -1 is not equal to 1. So this means we're looking at the other part of the solution. So the solution is of this form, -1 over x plus a constant, -1. So let's find out what the constant is for this initial value problem. Well, here it says y of 0 is equal to 1. So this means when x is equal to 0, so I plug in x is equal to 0, y of 0 is equal to 1. So I plug in 1 for y. So this means that 1 is equal to -1 over 0 plus the constant, -1. So by solving this equation for c, first I add 1 to both sides of this equation. So I get 2 is equal to -1 over c. So this means that c is equal to -1/2. So we found out what c is. So the solution of this initial value problem is -1 over x minus 1/2. So I replace the constant by this constant here by -1/2 -1. So this is the unique solution of this initial value problem. Any question up to here? So this is a good way of solving it. First, find the general solution, and then find the correct value of the constant for the initial value problem if you're given initial conditions. So this value of c corresponds to the initial condition y of 0 is equal to 1. So any question up to here? So here's a different initial value problem for the same equation. So y prime is y plus 1 quantity squared, and the initial condition here is y of 2 is equal to 0. Okay. So again, this is not the constant solution minus 1, because we're given the initial condition y of 2 is equal to 0. So if this were the constant solution minus 1, then it could never be 0. So it's not the constant solution minus 1. So this means we're looking at this other formula. The solution is of the form minus 1 over x plus c minus 1. And we need to determine the correct value of c for this solution. So y of 2 is equal to 0 means when x is equal to 2, y is equal to 0. So we plug in 2 for x and 0 for y. And we got this 0 is equal to minus 1 over 2 plus c minus 1. Okay, so I guess I added, so what did I do? Let's say I added 1 to both sides. So I got that 1 is equal to minus 1 over 2 plus c. So this means that 2 plus c is equal to minus 1 when I multiply by 2 plus c. So then solving for c, we get that c is equal to minus 3. So for this initial value problem, the constant is minus 3. And I replace the constant here by minus 3. And the solution is minus 1 over x minus 3 minus 1. So the solution, again, exists, is unique, and it corresponds to the value of the constant minus 3 in this form. So any question here? So now let's solve the initial value problem. Y prime is equal to y plus 1 squared. Y of 0 is equal to minus 1. So in this case, we could try, and here I try to use this formula, minus 1 over x plus c minus 1. And when we try solving for c, we'll see that it doesn't work. So here for the initial condition y of 0 is equal to minus 1, we're actually in the second case, and we'll get that the solution is the constant function minus 1. But let's try to see whether there is any c that works. And again, we'll see that there is no such c. So y of 0 is equal to minus 1 means that when x is equal to 0, y is equal to minus 1. So I plug in minus 1 for y and 0 for x. So we get that minus 1 is equal to minus 1 over 0 plus c minus 1. So the minus 1 cancels from both sides, and we're left with minus 1 over c is equal to 0, or 1 over c is equal to 0. Well, there exists no real number c such that 1 over c is equal to 0. Whenever you divide 1 by a real number, you get a non-zero answer. Well, and 1 over 0 just doesn't work. So no c exists. If we try to use the first formula here to solve the initial value problem, then we get that no c exists. So the true answer is that this initial value problem has a solution, the second part of the general solution, y of x is equal to minus 1. So we notice here that even though no c exists, this doesn't mean that no solution exists. again, there is this general existence and uniqueness theorem that guarantees that the solution exists and is unique. So our being unable to find C just means that the first formula is not the right formula to use. And on the other hand, we can use the second formula. So these sorts of special solutions that you get, for example, in this case, that you get for the special case when you would have been dividing by 0. So these special solutions are called singular solutions. So in this case, the solution consists of, the general solution consists of this general formula or this particular case. And the particular case is called a singular solution. And for this initial value problem, it turns out that the singular solution is the right solution. So any questions after here? Right, let's consider another equation. So I wrote this one in Leibniz notation, dy over dx is equal to y minus y squared. So let's solve this using the Leibniz notation. So we divide by y minus y squared and formally multiply by dx. So dy over y minus y squared, because we divided by y minus y squared, is equal to dx. And this equation is also separated because we have only terms containing y on the left-hand side and only terms containing x on the right-hand side. So as you can see, dy over y minus y squared on one side and dx on the other side. And this equation is written in differential form, as you see. So we have dy on the left-hand side and dx on the right-hand side. So there's nothing wrong with using the differential form. Anyway, so now we integrate both sides. And we get integral of dy over y minus y squared is equal to the integral of dx. So there is no special reason why I chose to solve this equation using the Leibniz form and using dy and dx, whereas I used the other method for the other equation. I just wanted to show you examples for both methods. We could have also done it the other way around. So now let's compute the integral of dy over y minus y squared. In order to do that, we need to use the partial fraction decomposition for the left-hand side. So 1 over y minus y squared is equal to 1 over 1 minus y plus 1 over y. So this is what you get if you use the partial fraction decomposition. And then we know how to integrate dy over y minus y, and we know how to integrate dy over y. Both of them give natural logarithms. So the integral of dy over 1 minus y is minus natural log of absolute value of 1 minus y. The integral of dy over y is the natural log of absolute value of y. So, and then this is only up to a constant. So I wrote here plus C2. And the integral of dx, well, so this just means the integral of 1 dx. So the integral is x plus a constant. And then if we have these constants on both sides, we should only keep their difference. So 2 constants are too many. We take their difference and we're left with C3, which is C1 minus C2. So I mean, we subtract C2 from both sides and we're left with this. Okay, so So actually, let's go back and look at this. So now I have a natural logarithm here. So I'm going to take the exponential in order to get rid of the natural logarithm. So exponential of logarithm of something is equal to that something. By taking the exponential, we get rid of the natural logarithm. So on the left-hand side, I got rid of the logarithm by taking the exponential. And on the right-hand side, I have, so again, we have to take the exponential of both sides. So on the right-hand side, I have e raised to the x plus c3. So then e raised to the power, to a sum of two things, is equal to e to the first thing times e to the second thing. So e to the x plus c3 is the same as e to the x times e to the c3. So e to the c3 can be any positive real number. Again, it's a constant. And I denote it by a new index. So instead of writing e to the c3 all the time, I'm just going to write c4. So now we have absolute value of y over 1 minus y is equal to c4 times e to the x. So then if absolute value of y over 1 minus y is equal to this, then y over 1 minus y is equal to plus or minus this. So this was almost the last step. I mean, getting rid of the absolute value. So now plus or minus C4, it turns out, is again a constant. It can, I zero here C3 for some reason, but so plus or minus C4 is either C4 all the time or minus C4 all the time. It cannot be C4 half of the time and minus C4 the other half of the time. The reason for that is that this constant is a non-zero number. So e to the C3 is equal to C4, which is a strictly positive number. So it's a non-zero number. And therefore, it cannot jump from a strictly positive number to a strictly negative number without going through zero. So this is why it cannot be C4 some of the time and minus C4 at other times, because C4 is strictly positive, minus C4 is strictly negative, and it cannot jump from strictly positive from strictly negative without going through zero. And it can never be zero, because C4 here is a strictly positive number, and e to the x is also a strictly positive number, so it can never be zero. So what this means is that it's either plus C4 or it's minus C4. It's not C4 some of the time and minus C4 some other time. So, okay, so finally we have this constant C5 here. And so since C4 is non-zero, this means that C5, which is plus or minus C4, is also non-zero. Okay, so we got this equation y over 1 minus y is equal to C5 times e to the x, where C5 is a non-zero number. Now we solve for y. So I multiplied both sides by 1 minus y, and I got that y is equal to C5 e to the x minus C5 e to the x times y. So that's because I multiplied both sides by 1 minus y. Okay, and now I group together the terms containing y. So y times 1 plus C5 e to the x is equal to C5 e to the x. And finally, I divided by 1 plus C5 e to the x, and I got this, that y is equal to C5 e to the x over 1 plus C5 e to the x. And this is called a sigmoid curve, as we'll see a little bit later in the course. So now, exactly the same as for the other equation. In the first step of our solution, when we divide it by y minus y squared, we missed a couple of solutions because we can only do this when y minus y squared is non-zero. So separately, we need to consider the case y minus y squared is equal to 0. This is a quadratic equation in y. It has two solutions, either y is equal to 0 or y is equal to 1. And it turns out that the constant functions y of x is equal to 0 and y of x is equal to 1 are solutions of the equation. So this is the general solution of our equation now. We have the formula that we got on the previous page, c5 e to the x over 1 plus c5 e to the x, where c5 is a non-zero number. Together with these two special solutions, y of x is constantly 0 and y of x is constantly 1. And you can note here that actually the solution y of x is equal to 0 is a little bit less special than the other one because it can be obtained from the general formula if we allowed c5 to be 0. So it turns out that, so if we plug in c5 equals 0 in this formula, then we get 0 e to the x divided by 1 plus 0, which is 0. So it turns out that this restriction that c5 cannot be 0 only happened because of the particular way we used to solve the equation. And actually c5 can be 0. And this just corresponds to a valid solution that's written here. Y of x is constantly 0. Please go ahead.
When you say check the solutions y of x equals 0, y of x equals 1, you need to check the solution that we have down there with c5, or
No, I mean checking the equation, checking this equation.
just plug
Yeah. I mean, if you are sufficiently confident in your computations, then you don't have to check. But this is just like an exercise I'm telling you during the course. Yeah. So in this case, for example, if you plug in y is constantly 1, so for example, this solution, y of x is constantly 1, then on the right-hand side, y minus y squared is 0, because 1 minus 1 squared is 0. And on the left-hand side, derivative of a constant, so y of x is constantly 1, is also 0. So the derivative of a constant is 0. So you get that 0 is equal to 0. So indeed, this checks that it is a solution. All right, maybe one more or a couple more. I think I have a couple more examples. So y prime is equal to 1 minus e to the minus y. Okay, so again, this is a separable equation. So on the right-hand side, you have a function of x times a function of y. The function of x actually is missing, but you can write this as 1 times 1 minus e to the minus y. And you can take the constant 1 to be the function of x. And to separate it, we divide the whole equation by 1 minus e to the minus y, and we get y prime over 1 minus e to the minus y is equal to 1. So now it's separated. We have all the terms involving y on one side and all the terms involving x on the other side. So again, there is no x explicitly in the equation, but the constant function 1 here can be considered to be a function of x. And we have, okay, so let's integrate both sides as functions of x. So we have integral of y prime over 1 minus e to the minus y dx is equal to integral of 1 dx. So y prime dx here is equal to dy. This is the substitution rule for integrals. So we made the substitution from the integration variable x to the integration variable y. And on the right-hand side, the integral of 1 is just x plus a constant. And again, y prime dx is equal to dy from the substitution rule. So all right, so now we want to compute this integral of 1 over 1 minus e to the minus y. This is the way that I computed it. I multiplied both the denominator and the numerator by e to the y. So this is integral of e to the y dy over e to the y minus 1. And we need to make a further substitution. So I let z be equal to e to the y. So then dz is e to the y dy. So again, in the substitution rule, if you have that z is a function of y, then dz is the derivative of that function times dy. And the derivative of e to the y is itself as a function of y. So the derivative, if you consider e to the y as a function of y, its derivative is itself. So then when you make the substitution, e to the y dy becomes dz, and e to the y minus 1 here on the denominator becomes z minus 1. So you have natural log of absolute value of z minus 1. Right? The integral of 1 over z minus 1 is natural log of absolute value of z minus 1 plus a constant. And let's go back to e to the y, because we are interested in solving this equation in terms of y. So we're still solving this equation. So the unknown function is y. So we replace z by e to the y, and we get natural log of absolute value of e to the y minus 1 plus a constant. So natural log of absolute value of e to the y minus 1 plus a constant is equal to x plus another constant. So that was from the previous page. Here, it's equal to x plus a constant. Okay. So then, again, we have too many constants. We can subtract one from the other, and we get that natural log of absolute value of e to the y minus 1 is equal to x plus c3, which is the difference c1 minus c2. So now I take the exponential of both sides. So absolute value of e to the y minus 1 is equal to e to the x plus c3. So taking the absolute value of the natural logarithm gets rid of the natural logarithm. Then we get rid of the absolute value, and we have e to the y minus 1 is equal to plus or minus e to the power c3. And I don't know why there are so many typos, I think. Probably this is not the right version of this file. So this is plus or minus e to the power c3. It's not ec3, it's e to the power c3, e to the x. So this means that e to the y is 1 plus, and then I replace plus or minus e to the c3 by c4 times e to the x. So again, it's either plus e to the c3 or minus e to the c3 all the time. It's not e to the c3 some of the time and minus e to the c3 some other time. And again, this is by continuity. So this is because e to the c3 is strictly positive and minus e to the c3 is strictly negative. And you cannot jump from a strictly positive to a strictly negative function without losing continuity. Okay, so now if e to the y is 1 plus c4 e to the x, then we take the natural log of both sides and we get that y is natural log of 1 plus c4 e to the x. where C4 is a non-zero number. And again, we have to check whether we lost any special solutions when we divided by 1 minus e to the minus y. So we lost track of the special case 1 minus e to the minus y is equal to 0. Right, so we cannot divide by 0. Okay, so if 1 minus e to the minus y is equal to 0, then we cannot use the previous method. We have to consider this case separately. And what happens if 1 minus e to the minus y is equal to 0? It means that e to the minus y is equal to 1. And then this means that e to the minus y is equal to the natural log of 1, which is 0. So it means that minus y is equal to the natural log of 1, which is 0. So it means that y is equal to 0. And it turns out that the constant function 0 is a solution of this ordinary differential equation. So again, maybe let's check what happens if we plug in the constant function 0 on both sides. The derivative of a constant function is 0, so y prime is 0 again. And 1 minus e to the power 0 is 1 minus 1, which is 0. So yes, the constant function 0 is a solution of this equation. So the solution is either natural log of 1 plus C4 e to the x, where C4 is a non-zero number, or it's the constant function 0. But it turns out that we can write both of these solutions together, in this case, just by allowing C4 to be 0. So it turns out that the restriction that C4 should not be 0 only came because of the way we solved the problem. And if we actually allow C4 to be 0, this just gives us the valid solution y of x is equal to 0. So we can write, in this case, we can write all the solutions using just one formula, namely natural log of 1 plus C4 e to the x, if we allow C4 to be any real number, including 0. All right, so I guess this is an example of an equation written in differential form. X dx plus y dy is equal to 0. So this equation again is separable. In order to separate it, it's enough to write all the terms containing y on one side and all the terms containing x on the other side. So this can be done by subtracting x dx from both sides. Or it could also be done by subtracting y dy from both sides. So here I subtracted x dx from both sides and I get y dy is equal to minus x dx. So now we can integrate both sides. So integral of y dy is equal to minus integral of x dx. So here I wanted to make this observation that, for example, let's consider this equation. Y plus y prime is equal to minus x. Even though it looks like this equation should be separable because we have all the terms involving y on one side and all the terms involving x on the other side, it's not separable. So this does not fit the definition of a separable equation. So the reason for that is that it should be a product on both sides. If you had y times y prime is equal to minus x, then it would be separable. But if you have y plus y prime is equal to minus x, it's not separable. It does not fit the definition of a separable equation. which, if you remember from Friday's course, is an equation that can be written in the form y prime is equal to a function of x times a function of y. So here you have y prime is equal to a function of x plus a function of y. That's not separable. So, right, if we subtract y from both sides here, you get y prime is equal to minus x minus y. So that's a sum. It's not a product. So it's not separable. Okay, so what about the equation that we are actually going to solve? So this equation so x dx plus y dy is equal to 0. This is an equation written in differential form. And if you formally divide by dx the equation, then you get x plus y times dy over dx, which is the same as y prime, is equal to 0. So this is how this equation would look like without the differential notation. It would be x plus y prime is equal to 0, which is the same as y prime is equal to minus x. Or you could also write it as y prime is equal to minus x times 1 over y. So it's clear that it's a separable equation. Okay. Anyway, so this is just about whether it's separable or not. But now that we know that it's separable, like I said, integrating both sides, the integral of y dy is y squared over 2 plus a constant. The integral of x dx is x squared over 2 plus another constant. And the second integral has a minus in front, so it should be minus x squared over 2. Okay, so x squared plus y squared is equal to a constant, which is 2 times c2 minus c1. So this is the equation of a circle, or whatever. And so this overall is the equation of a circle, but the graph of the solution is either the upper arc or the lower arc of the circle, because a circle does not describe a function, only each half circle describes a function. Let's see, I guess one more example here. Dy over dx is 1 over 1 plus e to the y. So here I separate the equation. 1 plus e to the y dy is equal to dx. So we now integrate both sides. Integral of 1 plus e to the y dy is equal to integral of dx. So the integral of 1 plus e to the y dy, so it's important that it's integral dy here, because we don't know what the integral of 1 plus e to the y dx would have been. We just know what the integral of 1 plus e to the y dy is. So this is y plus e to the y, right? The integral of 1 is y. The integral of e to the y is itself. And the integral of 1 is x. And then we have a constant on the left-hand side, a constant on the right-hand side. And in order to skip one step, I only wrote their difference. So c is the difference of the two constants. So this is the solution of the equation in implicit form. If we wanted to completely solve the equation, so in order to find out y, we would need to know how to solve this algebraic equation. Y plus e to the y is equal to something. So there is no formula to solve this type of equation. There is no such thing like the quadratic formula for this kind of equation. So this is the best that we can do. It's so you cannot say that y is equal to whatever arctangent of e to the x plus 3 or whatever. So this is the final form of the solution. This is called the solution of the equation in implicit form. So the solution in implicit form is when you have this algebraic relation between x and y, but you're unable to go further and find out y explicitly as a function of x. So in these cases, when we are unable to proceed further, we stop here. So this is the final solution in implicit form. Okay, let's see. So I see that I have one more example. Well, I guess I'm going to go very quickly over this one. Y prime is equal to sine of y. Y prime over sine of y is equal to 1. This is now separated. So integral of y prime over sine of y dx is equal to integral of 1 dx. I make the substitution from x to y on the left-hand side, and then y prime dx becomes dy. And then we need to compute the integral of dy over sine of y here. After a complicated computation, we get a complicated answer. So it is 1/2 natural log of 1 minus cosine y over 1 plus cosine y plus c2. So 1/2 natural log of 1 minus cosine y over 1 plus cosine y is equal to x plus a constant, which is the difference of c1 minus c2. And so here I just wanted to give you an example of a complicated answer. So I told you that all the previous ones were relatively straightforward. So here is how a complicated one looks like. Y is equal to arc cosine of 1 minus c4 e to the 2x over 1 plus c4 e to the 2x. So the point that I wanted to emphasize here is that sometimes even when we are able to solve an equation, it's not always worth the effort, because sometimes we get a complicated formula for the solution. And then there are other ways that are better suited to understand these equations, like the phase line method that I mentioned, which we are going to use later. So even though we know explicitly the formula for the solution, the formula can be so complicated that it's hard to understand what it actually does. And this is the final example for today. Thanks for your attention. Please let me know if you have any questions, probably by email, and see you next time. What about the class on Friday, sir?
Is it in person or online?
It's online, it's recorded.
This coming Friday, can we have in person?
It's all online. The classes on Friday will be online.